Hello students, in this session we are going to discuss about combination of cells. So we'll combine the cells, one in series connection, another in parallel connection, right? So let's first study about the combination of cells in series connection. So the first we are going to discuss series connection, right? So while dealing with the series connection, first let us draw a simple circuit. Let's say this is my external resistance, alright, R, okay, now which is connected to the series connection of cells. Now this is the cells which are connected in series like this, okay, right. Now let us say in this particular connection R is our external resistance, R is external resistance, right. Now let's say small r be internal resistance, small r be internal resistance of each cell, alright, and we also let's say capital E be EMF of each cell, right, and let there be n number of cells that are connected in series. So n be the total number of cells. So we want to find out what will be the value of current. We want to find what is the value of the current that will flow through this resistance, external resistance I, right. We know from the definition of current, the current can be defined as I equals to total EMF divided by total resistance. So let's write RE, which refers to the external resistance, and for internal resistance let write R suffix I. Now first let us calculate what is the value of total internal resistance, alright. So we can see the internal resistance of each and every cell is given by small r, right, and all the cells are connected in series. So we can write all cells are in series, right. Now as all the cells are in series, R total, or we can say this equals to Ri, will be R plus R like this up to n number of R. So total internal resistance will be n into small r, alright. Now let us find out the total EMF. Now each of the cell is contributing E, capital E is the EMF of each cell, right. So we can write total EMF will be the summation of each and every EMF. Now for example, let us say this is a point A, there is another point B, there is another point C, right. Let's say the potential difference between A and B be V1 and B and C be V2, right. Now if someone asks you what is the potential difference between A and C, what will be the answer? Simple, it's V1 plus V2, right. So on the same logic we can say the total potential difference or the total EMF will be nothing but N into E, as there are n number of cells, right. So we got all the values what we require for this particular expression. So this is E total. So I can say the current that is flowing through this external resistor will be I equals to N times E divided by external resistance is capital R plus total internal resistance is N into R, right. So this is the expression for the total current that is flowing through the external resistance or flowing through the circuit when the cells are connected in series. Now let's discuss two limiting cases for this. Now the first limiting case, let us say the external resistance, that is capital R, is much greater than internal resistance, total internal resistance, that is NR. Okay. So in this case we can write, as we know the total current is I equals to N into E divided by capital R plus NR. So in this particular case we can ignore this NR terms, right? So we can write by ignoring this NE divided by R. Alright. So this can be written as capital I equals to N times E by R. Now just look at this expression. If there is only one cell of internal resistance very small compared to external resistance is connected in this circuit, having the EMF capital E, the total current that is flowing through the circuit will be only E by R, right? So when the internal resistance of cell is very small compared to capital R, we can say that is equal to the current equal to N times of the current produced, as if we are taking only one cell with the internal resistance very small compared to the external resistance, right? So you can write capital I equals to N times E by R. Okay. Now let's look at the second limiting case, number 2, where external resistance is very small compared to total internal resistance. So let's start from the same formula. I is given by N into capital E divided by R plus NR. Alright. So in this particular expression we can ignore this value of R. Okay. So we can write it as just NE divided by NR, that is equal to E by R. Alright. Now what is E by R? If there is only one cell connected to the circuit having internal resistance very high compared to the external resistance, then this is what the value of current that will be flowing through the circuit. So we can say when the external resistance is very less than the total internal resistance, the current flowing through the circuit is equivalent to the current that would have flown if you connect only single cell having external resistance, only single cell having internal resistance very high compared to the external resistance. So these are just the simple application of the simple limiting cases based on this formula. Now let's focus ourselves to the parallel connection, parallel combination of cells, right? So the second case will be parallel combination or parallel connection, right? So let's draw a circuit again, simple circuit having an external resistance R. Alright. Now there is a, let this be first cell, let this be the second cell, and like this there are n number of cells. Okay. Of each of having EMF capital E, and the current will flow in this direction, right? So again we can write in this particular case N be the number of cells, okay, capital R external resistance, alright, capital E EMF of each cell, alright. And what is the value of smaller? What is smaller? Smaller is internal resistance of each cell. Now the problem in this expression is also the same, that we have to find the current that is flowing through the external resistance R. So in this particular expression we can say I again equals to will be total EMF divided by total external resistance plus total internal resistance, right. So in this particular expression, see the EMF between these 2 points, if I say this point is A and this point is B, the potential difference between these 2 points will be capital E only, okay, as they are all in parallel connection. So we can write in this particular case E total will be equal to E. Alright. Now let's calculate the total internal resistance. Let's calculate this value. So total internal resistance, that is Ri, let's say be R dash. Okay. We have assumed that there are n number of cells that are connected parallelly. Okay. Let's say the effective resistance be R dash. So we can write, now when you connect all the cells in parallel, so what will be the value of resistance? Resistance will follow its own rule. The total effective resistance can be easily found out by just applying the formula for the resistance when they are connected in parallel, right. So I can write 1 by R dash is equal to 1 by R plus 1 by R up to n times, right. So from here we will get R dash equal to n by R, or 1 by R dash equal to n by R, right. So R dash can be written as R dash equals to R divided by n. Alright, so we got the value of Ri also. Now let's put the value in this particular expression. So we'll get current equals to E times divided by capital R, total external resistance is capital R, plus R divided by N. Alright, so just look at this expression. When the cells are connected in series, this is the value of the current that will be obtained, that is passing through the external resistance R. But when the cells are connected in parallel, this is the value of the current that will flow through the external resistance, right. Now again look at the limiting cases. So the first limiting case is, first one is if R is much greater than total internal resistance, or you can just say R, right. So if R is much greater than small r, we can ignore this term. So let's start with this term only, I equals to E divided by R plus R by N. So we'll neglect this term and we are left with E divided by R only. Now what is E divided by R? Similar to this particular case, when you connect a particular cell, only single cell having EMF capital E, and the internal resistance is much less than the external resistance. So what amount of current you will get? The same amount of the current you will get in this case only if you connect n number of cells each having total internal resistance that is quite small as compared to the external resistance, the value of the current you will get is same. Now let's look at the second case. Second case is when R is much smaller than total internal resistance. Now let's again start from this formula only. I is given by E divided by capital R plus R by N. Now we can discard this particular term capital R. So we will be left with E divided by R times N. Now what is this particular term E by R into N? So we can say that when we connect n number of cells parallelly having the total internal resistance much greater than external resistance, the current we will obtain is equals to n times of the current which we would have obtained when we connect the single cell having internal resistance small r, that is quite greater than capital R, right. So these two are the two limiting cases for the cells connected in parallel combination, right. So student, in this session we have seen what is the value of the current that we have obtained for the circuit if we connect different cells, one in series combination, another in parallel combination.